It's my great pleasure to have Christian Lubich from University of Tübingen today to give a talk in the Distinguished Visitor Lecture Series. He has made many important contributions to numerical analysis, including the geometric integration for structure preserving algorithms and dynamical low-rank approximation. So for his outstanding work, he has won many awards, including the Dahlquist Prize by SCIAM, and he was a plenary speaker of the ICM in 2018. So today he's going to tell us something about time integration of tree tensor networks.
Oh, thank you for the nice introduction, and thank you for inviting me here. It's really a pleasure to be at this workshop and at this venue. I will tell you about time integration of tree tensor networks without explaining to you what tree tensor networks exactly are. But the basic idea is comes from the matrix case, where you approximate a huge matrix by a low-rank matrix. So suppose we're given here a matrix A, which is, well, it doesn't look so huge, but it is huge. And this can be factorized using the singular value decomposition. And if I truncate the singular value decompositions, so I would get something with a matrix U, which has orthonormal columns, but say only a few of them, if the approximation is by a matrix of low rank, then I would have here a matrix V transposed, where V also has orthonormal columns. And in the SVD would have a diagonal matrix in between, but here just let me take a small matrix S by S, and if R is the rank here, then this would just be an R by R matrix, so this would be small. And if you really would like the singular value decomposition, you would just compute the singular value decomposition of this small matrix S. Now, approximating a huge matrix A by a low-rank matrix makes a lot of sense if the singular values decay reasonably fast. And one thing to notice for later is that if I truncate here, then the error will essentially be determined by the largest singular value that I chop, which would typically be roughly of the same size as the last one that I retain. This will be an important notion forever. But now in the title you see tree tensor networks and time integration, so what has this to do with that one? If we have a tensor instead of a matrix, so a 3 tensor would correspond to a cube, and then you would have a hypercube. You can also try to find a low-rank format which represents a tensor in some way, and this would correspond to in a schematic description. You would represent this by one such way is to give some tree structure. At the leaves, you would have the physical degrees of freedom, which would correspond to U and V in this case here. So we start with U1, U2. Here you have basis matrices, which are somehow of the same type as here. But then there are connection tensors which form this together. So the data here are matrices with orthonormal columns at the leaves and interconnection tensors in between. And of course, there are different ways that you can find, that you can connect given leaves by trees. This would be the tallest tree. This would be the lowest tree in a way. And now I say time integration, so the rest here will be when A depends on time. And then the question is, how would I update this? Even if A of t is given explicitly, to compute this lower rank factorization here, I would have to compute the SVD at every time point. And this is far too costly. So we need a fast updating procedure if A of t is given explicitly, but the interest here will be when A of t is not given explicitly, but is itself the unknown solution of a differential equation. Typically think of something like the Schrödinger equation. So that was a long introduction. Now I have to speed up. So here's the outline. Well, this was, we'll come to that. So dynamic low-rank approximation will play an important role. And my talk will be built in that way that I explain you the concepts and basic results in the matrix case. Just because everyone is familiar with the matrix formalism, whereas here I would have to introduce some formalism which would take me half the talk. Then I will explain you all the basic ideas in the matrix case. And the matrix, well, that's the smallest conceivable tensor network. So my talk will be mainly about this tree tensor network. But then ultimately the message is, and everything what I tell you about the matrices will generalize both in the construction of the algorithms and in the properties of the algorithm to general tree tensor networks. So the tree structure will be important, so we must not have loops in these networks. So that's the program of my talk. And just as a motivation, let me begin with a numerical experiment that came up in recent collaboration with quantum physicists. So they want to study the dynamics of quantum spin systems, and here is one such. It's given by a discrete Schrödinger equation on a finite dimensional space. So you have d particles, and to each particle corresponds a two-dimensional Hilbert space, the complex number squared. And it's a Schrödinger equation with a complex imaginary unit I in front of this, and here H is a Hamiltonian, which is built up from these Pauli matrices. And here's an interaction, here's a nearest neighbor interaction. So there are d particles aligned in a chain, and here's a nearest neighbor interaction between the two. The details are not very important, but you can think as the particles being aligned here, and then I can form different tree tensor networks with that. And what we have developed is a time integration algorithm, well, for such differential equations in high dimensional spaces. So you see, C square, of course, is a very low dimensional space. It's two-dimensional. But take this to the power d and think of d something like they would like to have 32 or 64 or even more particles. You get to quite high dimensions. So this is a finite dimensional ODE, but in high dimensions because we want to have many particles. Now it's a quantum spin system. So it's in quantum physics, this is a very a simplified model of some more complicated things where just consider the spins, which sometimes is the only relevant thing when it comes, for example, studying magnetization effects. Then these are very widely used models. So the goal would be to approximate the wave function. If you don't like the quantum spin system, take just a molecule. That's fine too. There you would have higher dimensional spaces at infinite dimensional Hilbert spaces, L2 spaces there. But in a way, it's a simpler model, but it has the same algorithmic difficulties. I mean, it's just the high dimension which you have to fight somehow. So what we will do is to approximate this psi of t. Well, which would here just correspond to a 2D dimensional tensor. We approximate it by such a 3-tensor network where the only data are basis matrices, which are here 2-dimensional at every leaf, and then you combine them with connection tensors, which give the correlations between the particles. And we have developed such an algorithm, and let me tell you about some, well, here we consider it with different trees, which are just the ones that we had here, except here it's 16, here it was 8. So here we consider the tree of minimal height, or which is a so-called balanced tree, or you consider the tree of maximal height, which corresponds to tensor trains or matrix product states in the physics literature. And we have devised an algorithm which changes these ranks adaptively and integrates it. And we have applied the same algorithm to 2 different trees. The question is, of course, which tree should I choose? This is not known a priori, and it can be helpful if you have a rank adaptive integrator, and if you trust the rank that is chosen by the integrator to decide between different tree topologies. And that's what we did here. And what we considered is just the developments of the rank, the maximal ranks in time. And there's the blue curve, that's one of the trees, and there's the red curve, that's the other of the trees. And here the rank was kept at limited to 200. That was the maximum rank that we were allowed. You see, these curves are quite different. It's not only the ranks, it's also the number of independent parameters that evolve in time, which are very different for the 2 ranks. Now, I've shown these pictures at other talks before, once before a physics audience, once before a mathematical audience. What would you guess? Which one is which? Which is the better one? The balanced tree or the long tree? We have a system with nearest neighbor interactions. You can is there a physicist here? What would you guess? Okay. What is there? Well, there are mathematicians here. Any guess there? So my experience was physicists would always choose the matrix product state because that's very popular in the physics literature. Mathematicians would always choose the balanced tree. And I'm a mathematician, of course, mathematicians are right here. So this is for the balanced tree. The point here in my talk is about this is just one example with one particular experiment. There's no general statement that can be done on basis of just one such picture. But the point here in my talk is rather, how do you get such pictures? What is the methods? What are the methods behind? What are the computations? And what numerical analysis is available for such methods? And that's what my talk is about. So this is the end of the motivation. Now we come to this dynamic low-rank approximation, and for almost all of my talk, except the last slide, I will consider this matrix case, where we have a differential equation for a huge matrix A of t, and we want to find an approximation of low rank evolving in T. And then there's the question, what are the differential equations, say for these factors U, S, and V, and also what are suitable time integration methods, or can I just use standard methods? And so the setting is the following. I have a matrix differential equation for a matrix A of t, which is huge, too large to handle. And I want to approximate it by something which I call y of t, which is of rank R, and these matrices of rank R, they form a manifold. And the question is, how should I do that? How should I do this? Well, first of all, why would I like to approximate by a manifold by matrices of rank R? I think this became obvious from here. If I have an m by n matrix here, I would have m times n elements, whereas here I would have m times r and n times r. So it's essentially m plus n times a small number. So you have a huge gain in memory and, of course, also in computations, because you do not, provided you can only work with these factors then. Now, the question is, how do I compute such an approximation? And what we do here is, well, suppose we are already at some approximation y of t, and then the question is where to go. So I need to determine the time derivative of y. If I want that y of t stays in this manifold, then it must be in the tangent space. And I choose the time derivative as that element in the tangent space, which is as close as possible to the right-hand side of our differential equation, evaluated at the current approximation. And I choose the Frobenius norm here. So this f is not the same as this. This is Frobenius, and this is our f here. So this would be a minimum defect y dot minus f of y would be the residual or defect in our differential equation, and then minimize this with respect to some inner product norm for which I choose the Frobenius norm. But this is equivalent, just by writing down the minimization condition here, that the residual or defect is orthogonal to all elements in the tangent space. And this you can view as a Galerkin method. Residual is orthogonal to our approximation space. The approximation space here would be the tangent space, but there's a twist to it because we don't have a fixed approximation space. The approximation space here is the tangent space, which depends on the current position. So even if you start from a linear differential equation here, you will then end up with some nonlinear process here. It's a kind of nonlinear Galerkin approach. And another formulation is this just means that y dot is the orthogonal projection of f of y onto the tangent space. Here's a picture. We have here a manifold, which would be a sketch of our rank R manifold. We are sitting at an approximation point y. The time derivative would be f of the vector field would point out of the manifold. We project it down onto the tangent space and then take the projection as our new velocity. And this has a long history. In 1926, Schrödinger formulated his famous equation, which immediately caught the attention of the physicists of the time. And they also immediately noticed that it's a wonderful equation, but how do we draw information from out of it? And what Dirac did, essentially, he approximated this wave function, which depends on on the coordinates of the particles by something which is a product of single particle functions. Well, he actually antisymmetrized this because he considered fermions, but basically this was the idea. And then he just wrote down if you make such an approximation, which is called a Hartree approximation, which is not a good approximation, by the way, but it somehow corresponds to the rank 1 case in the matrix. So if you think d equal 2, you would here this one vector times another vector. So this would correspond to a rank 1 matrix or rank 1 tensor, then in the D case. But then the question is, if we want to have such an approximation, how should we approximate, how would you determine these functions phi1 to phi d? And he just wrote down what we did, which was the analog of this formulation. We assume that this holds. And from this he determines then the functions. And yeah, so this has a long history in quantum physics. Now, to really work, I mean, the formulations I gave here are quite abstract. You work on the tangent space, you have some rank R matrices, but how do you actually compute with them? And the interest, of course, is in a decomposition as I had it here, as U, which are just a few vectors which are orthonormalized, then a small matrix R by R S, and V transposed. And to have rank exactly R, I need to have this inner matrix invertible. And of course, the interest is that the underlying problem allows me to choose a rank R, which is much smaller than the dimensions that are given. And that's where the big gain comes from. So we take our original matrix differential equation, we approximate it by the one which is projected to the tangent space at the current approximation. We write our approximation in such a form, factorized form, and use this to approximate the unknown matrix A of t. And if you work this out, you get differential equations for the factors for U, for V, and for S. For S, well, that just looks like a standard Galerkin method in the basis U and V on the right-hand side. And in the differential equations for U and V, there's some projection out of the range of U or V. But then there's the S inverse appearing here. And that is a pain. Why? I told you, to get a reasonable approximation, I truncate the singular values. And essentially, the last one, the first one that I truncate, that determines somehow the error. But then the last one that I do not truncate is typically of the same size, slightly larger, or if there is a gap, I wouldn't know where the gap is. So I must expect that this matrix S has small singular values, which means it's ill-conditioned, but it appears here, its inverse appears on the right-hand side here. And that's a problem, because yeah, as I explained to you, this S is typically ill-conditioned, so the R singular value of S is much, much smaller than 1. Now you can think maybe this is not a good factorization, and also this differential equations are not unique, but here we impose some gauge condition which says that U transpose U dot is equal to 0. So maybe you can avoid this in a different formulation. No, you cannot. Because it turns out that 1 over the smallest singular value corresponds to the curvature of our rank R manifold at the current point. And I'll show you. I've brought with me a manifold. Here it is. So this is a manifold with moderate curvature. You agree? This is not. This is high curvature. There are ridges where there is very high curvature. But now, what are we doing? We follow the tangent space along our manifold. but this has high curvature. Would you trust the numerical method that follows the tangent space along such a manifold? Probably not. So have physicists been stupid since Dirac's time? Even as a mathematician, I wouldn't dare say that. No, they are clever people. And they have used it, and it works. So what's wrong? We have a high curvature here. We have high curvature here. You wouldn't trust using this Dirac-Frank variation principle, which we used before, to get an approximation. Well, the problem is this is a very bad model for a low-rank manifold. I'll show you a better one, which is actually from the collection of our geometrical objects at Tübingen. It's a 19th century ruled surface. Well, you just see it's some curved object, and it's built up of straight lines. You're perhaps more familiar with a hyperboloid. So think of a hyperboloid here, which is almost a cone. You have extremely high curvature here. But this is built up of flat subspaces. And now imagine if you're going along such a straight line, you can pretend to be blind to the high curvature here. You just don't notice it. You just go along the straight line. And that's the key to explaining why the methods based on our time-dependent variation principle work for these low-rank manifolds. And I will explain that. We will find integrators which have the property that in each of their substeps, they only go along flat subspaces. And that's what saves the day. I mean, I was very much appealing to your intuition now, but all this can be made rigorous, and we have done that. But it's really that these low-rank matrices have flat subspaces. That's a key property that saves us, despite of having these high curvatures. And we've come up with different numerical methods, and I would like to the first one was in joint work with Ivan Ozeledets in 2014. Here I have recalled the different formulations that we have had, and they are all equivalent. This maybe looks as the most abstract one. We project onto the tangent space. But it turns out to be, in a way, the most practical one, because you can give this projection explicitly in the case of such a low-rank manifold. And it's just built up. You needn't even look very careful of it. You see it's an alternating sum of three terms. When a numerical analyst from this community sees a differential equation which has two or even three terms, the first thing you do, you split. That's what we did. We split this tangent space projections. And it turns out that each step can be solved explicitly if A of t would be given, and can be solved by a standard numerical method like a Runge-Kutta method if A of t comes from a differential equation. So we split the projection, and well, I think to this community I need not explain much. We first integrate the first term, then integrate the second term. Note that there's a minus sign. This will be some importance later. And then there's the third one. Now, in this abstract form, it's not useful, but it turns out that this can be done in some quite simple steps. And let me just show you the first and second one. The third one is orthogonal. So the trick is you form we do not evolve U. U has orthonormal columns. It's not on a flat subspace. But we take U together with S. And this is just the subspace of M times R matrices. And so I take U and S together, call it K. And I consider the projection of the differential equation onto the range of V. And so I get a differential equation which is of the same dimension, matrix differential equation which is of the same dimension as a U. So it's only a slim matrix, not a full matrix. And this I integrate. And this is an integration in a flat subspace. But then, of course, I do not yet have, at the end of the day, I only get an approximation to K, so I have to get back to an orthonormal factor. But there's no need to integrate a differential equation for that. I just do a QR decomposition and get this orthogonal factor. So it's a method, and that structure is quite typical. I have an evolution, and then I have an orthogonalization. And this always alternates. And then for S, it's easier. It's just the Galerkin method on the subspace created by U1 and V0 in this case. And then for L, I take V and S together and integrate in this way. And after these three steps, I get a new factorization which approximates my solution. Now, let me come to back to these small singular values. I mean, they are really the critical thing here in all this theory. So recall there was this S minus in the differential equations for U, V, and S. And notice that in the algorithm that I just presented to you, the S minus never appears. Of course, there's the QR factorization, which becomes somewhat wiggly if I have a matrix with nearly linearly independent columns, but that's much milder than here. Now let me give you a numerical experiment for a matrix which has geometrically decaying single values, like 2 to minus j, and j ranges from 1 to 100. And on the left-hand side, I apply a Runge-Kutta method. On the vertical axis, there's the error. And on the horizontal axis, there's the time step size. And for rank 4, so I choose a fixed rank 4, the Runge-Kutta method just works fine. If I go to rank 8, I have to limit my step size. If I go to rank 16, I have to limit my step size much more further. And for higher ranks, I have to use extremely so small step sizes, which are bounded by the smallest singular value. So I get an extreme step size limitation. The more accuracy I require, the smaller I must use my step sizes, not for accuracy reasons, but really for stability reasons. What's not plotted here is if you go beyond the rightmost points here, the method just becomes unstable. And you would have the same if you would apply an implicit Runge-Kutta method. You wouldn't get the instability, but it would just be plainly wrong, which is not that much better. On the other hand, this projector splitting integrator that I showed you, well, I presented to you in this first order Lie-Trotter form. You can also make a Strang splitting out of it. But let's keep it to that. And you see, you get good approximations. Note there are different scales on the left-hand side, which are on the level of the best approximation error and you can use extremely large step sizes. You might wonder why in the last one for rank 64, the number goes up again. That's just round-off errors because we're here. And if you take more steps, you have more round of errors. So it turns out that in this example, this projector splitting integrator is robust to small singular values. The higher the rank is, the smaller singular values you have, but they don't bother this integrator much, whereas a standard integrator, any standard integrator, really suffers. Now, this is not just one example. We could prove a result which shows that this projector splitting integrator has a first order error bound that is independent of any small singular values. So these small singular values can be arbitrarily small and do not affect the error bound. And we'll give you the exact formulation. Of course, you need some assumptions, but I would like to mention the key properties in the proof. One is, and that's a very amazing one, that if our matrix A of T itself would be of rank R, and I would just consider the differential equation where I project the time derivative of this A of T, and then use this integrator, then it reproduces this low rank matrix exactly. That's an amazing property, which we only find by chance, by doing numerical experiments where we observed it. It's not something you would expect, but once we confirmed it in several numerical experiments, then the proof was not so long. But it's really an amazing property, and I must add, it depends on the ordering of the splitting. We have these three terms. If you reshuffle them, you don't have this property. So it was in this very peculiar ordering that I gave to you. And the other thing I mentioned already, the algorithm always works in flat subspaces in each of the substeps. And this means just going along straight lines in something like this hyperboloid. And as you pass through, you just don't notice that there is some trouble here. And this is made rigorous in this result together with Emil Chieri and Hanna Wallach, who were both in Tübingen at the time. So again, it's this ruled surface structure which saves the day. Now, we were very happy with this projector splitting integrator, and I'm still very proud of it. But just 2 years ago, we came up with an alternative, which you remember in this projector splitting integrator, we had these three substeps, which were one after the other. Now, here we do a basis update. The first step is identical to that of the projector splitting integrator. But then, in parallel, we do that for L, which is just the product of V with S, and update the basis here in parallel. And then I do a Galerkin method in the subspace generated by the updated basis. And so I have this basis update and Galerkin method, which has the nice acronym BUG, and everybody knows a BUG program. We constructed this systematically usually, but the bugs are not constructed so systematically as we do. So this was joint work with Gianluca Ceruti, who was a PhD student with me. Now, if you compare those, there's one thing, and that's important for parabolic problems. The projector splitting integrator has a minus sign here, which for a parabolic problem means going in the solving the heat equation in the backward direction. So you have an unstable substep within your algorithm, and you needn't have heard much of numerical analysis to know that this is not a good idea to construct that. So it has no backward step. So for strongly dissipative problem, that's important. It has also the property that if my matrix A would be symmetric or antisymmetric, skew symmetric, this BUG integrator would preserve this symmetry. That's important if you think here in applications to Schrödinger equation of fermions, which have such an antisymmetry, or bosons, which have a symmetry property. And this is preserved by this integrator or its extension to the tensor case. And also it has more parallelism. Here the left and the right bases are fully computed in parallel. They do not depend on each other. They can be computed in parallel. There are also negative things. It doesn't preserve the norm and the energy for the Schrödinger equation, which the projector splitting integrator miraculously does. Both the norm, that's easy, but it also preserves the energy. But the proof actually uses properties that we derived for the projector splitting integrator. Now that was just this bug integrator, which does a Galerkin method in the updated subspace. You could also do a Galerkin method in the old subspaces, and then get something which is fully parallel. All the differential equations that appear are in parallel. That's not a big issue for a matrix. But if you think of a tensor network, where we have all differential equations that appear at each of the nodes in parallel, there it can be a very substantial issue. Now let me come to rank adaptivity. How do you choose the rank? Now, if the rank is too large, that's easy to find, because then you just have small singular values there, and you reduce the rank. So reducing the rank is easy. But to increase the rank, you need information beyond the space in which you are working. And that's not so obvious. But it comes in very handy here, because we have the old basis U0, we have the new basis U1, so just put the two together, augment the basis, and this turns out to be a very good space, because it includes somehow the good directions. Just form in this space, of course, the differences are also in there, and differences corresponds to the derivative. So the differential equation somehow is incorporated here. And this works very nice. So we do the Galerkin method in this augmented subspace. And then at the end, when we have computed this augmented approximation, then we reduce the rank again. And this works very well. It's very simple to implement. Has a very nice geometric properties. If you do this, you retain the norm. You retain the energy up to this truncation that you then do at the end. But this augmented method preserves, again, both norm and energy. It allows the rank. Yeah, it has the same robust error bound like the projector splitting integrator. It preserves the norm up to the truncation tolerance that you do at the end. It preserves energy up to the truncation at the end. And in dissipative systems, for gradient systems, you would like to have the energy decay. So that's important for optimization problems. This is also preserved, and then of course you truncate, but this truncation that you do at the end is under control. Yeah, I'm almost in time. What I told you is about low-rank matrices. The title promises 3 tensor networks. The short message is everything I told you about matrices extends to 3 tensor networks. Now that's by no means trivial. From the picture, you can imagine that your tree is built up from these elements. But to translate this into a rigorous theory, not only for formulating the algorithms, but also for analyzing the algorithm, that's a lot of work. And it requires a formalism that I didn't want to present to you, because that would have filled my time up to now. But the steps are basically, you start from the known theory by now of lower rank matrices. From there, you go to what is called Tucker tensors. So they would correspond to bushes. Then maybe you add something more where you could have several dimensions here. So you have these extended bushes. And from these elements, you form then these trees in a recursive way. So that would be the program which has to be carried out and is very technical. Just a notice to the one physicist in the audience. Physicists like to draw pictures. These pictures really help the intuition. They are very useful. But you couldn't make a convergence proof just with these pictures. So you really need a rigorous formalism for that. And we have carried this out for the projector splitting integrator. This extends to 3 tensor networks. And also this rank adaptive bug integrator, basis update and Galerkin integrator, can be extended to 3 tensor networks. And these are some recent works. So thank you for your attention.
Thank you, Christian, for a fascinating talk.